is partly Gibbs. So continuing on the same theme, but we will now work with Gibbs sampling instead of complex Hastings, and it's not as simple perhaps as it sounds. It's not just replacing the image with a Gibbs sampler here, but it leads to some interesting properties, at least of the resulting method we're discussing. So the aim of this part now is to show you how Gibbs sampling can be used for state parameter inference, first of all. So we'll go back to similar to the previous lecture that we started with the ideal setting to drive some ideal MCMC algorithm that turns out to be intractable, and then we will see how we can exactly approximate this using SMC. So yeah, starting with Gibbs sampling, we'll introduce what's referred to as a conditional importance sampling kernel, which is like a stepping stone, could say, towards the particle Gibbs kernel. Then towards the end, I will talk a little bit more about some extensions of this. Okay, so Gibbs sampler, if we just take like standard Gibbs sampling, is that something that you're familiar with? A few nods here, but a few shakes, I think. So not everyone. So it's another way of constructing MCMC algorithms, a generic approach for MCMC, you could say. And the idea is essentially that in some problems, it can be difficult to design sort of an efficient Metropolis Hastings proposal, in particular if we're working with high-dimensional target distributions. Gibbs sampling, you can think about this way of turning this high-dimensional sampling problem into a series of lower dimensional sampling problems, each of which is hopefully simpler to solve. So as a very simple example of this, we can consider a target distribution. Now, this is again very generic. We have a target distribution pi over two variables, x1 and x2. You can also think about these as being kind of groups of variables. So each x1 and x2 here could be a vector as well. But in some way, we have split the coordinates into two groups. Then we can always factorize this joint PDF according to, on the slide here, into a marginal over x1 and a conditional over x2 given x1. And that also means that if I have now a sample from this joint distribution, x1, x2, then, well, clearly x1 will be distributed according to the marginal under this joint x1. And that also means that if I generate a new sample x2 star from this conditional, which is the second term in the factorization here, and then I consider this pair x1 and x2 star, that will also be distributed according to the joint. I think that's kind of an important part to understand this algorithm. So does that make sense to everyone? Clear? But that also then means that if we start with a sample from the joint, then we can kind of replace any coordinate in this sample by generating a new value from its corresponding conditional distribution. And this will still give us a sample from the joint. So this is now a way of constructing a Markov kernel, which has this desired property of leaving pi variant or having pi as statement. This is referred to as the Gibbs sampler. So the Gibbs sampler for this two-dimensional problem would just look like this. Okay. Yeah, so we just loop over the coordinates, and in each MCMC iteration, we first replace x1 by drawing from this conditional distribution here of x1 given x2, the previous value of x2. And then I update x2 by drawing from its conditional value. And note here that I condition on the most recent value of x1, so the one that I generated in the line above here. If I now apply this to just a simple toy problem, it's a Gaussian distribution, which is illustrated by this ellipse here. It will look something like this. So you see that each iteration here, well, I'm showing sort of both the inner steps of the algorithm as well. And then we see that each iteration we update one of the coordinates, and we're kind of stepping through this way. So similar to like a coordinate descent type algorithm for optimization, but it's now doing sampling instead. Okay, and as I said, we can now use this for constructing MCMC kernels. And just a reminder, this slide we had on the previous part as well. An MCMC kernel, it should be some conditional distribution over the next state, x star, conditionally on the current state x, which has this, satisfies these requirements of stationarity and ergodicity. And just as a note here to avoid any confusion, used color coding in both of these lectures, red and blue. It will now mean something different. So in the previous lecture, I used blue for states in the state space model and red for parameters. Forget about that. Now I will use, throughout the rest of this talk, this lecture, I'll use blue to denote sort of the current state and red to denote the next state in the Markov graph. From blue to red. So this idea of a Gibbs kernel, I showed you the case with two variables here, x1 and x2, but it can be generalized to arbitrary high dimensional distributions. So if we now assume that this pi is a distribution over d coordinates, x1 to xd, then we can construct a Markov kernel for moving from the blue x here to the red x star. So we see that we update all the coordinates, but we do it one at a time. So at each iteration here in this inner loop, we update coordinate xj by sampling from its full conditional distribution, conditionally on the most recent values of all the other variables. So it depends on where in the inner loop we are, but we sort of condition on x1 to j minus 1 star, because they have been generated previously in the loop. But for the remaining ones, xj plus 1 to xd, well, we use the input values here, the most recent ones. But this procedure will then also define a Markov kernel on this joint state, which has pi of x as a stationary distribution. There are some limitations and possible sort of extensions. Use of some of them, but just listing some of the key limitations and extensions. So one limitation here is that if there are very strong dependencies between any coordinates here, it can mix very slowly because we always condition on the other coordinates. And if that sort of brings a lot of information about the current coordinate that I try to update, I'm very constrained in how much I can move that coordinate. You can imagine this Gaussian example that I had. If this ellipse is very sort of thin, then I can only take very small steps as I step through that thin ellipse, which is corresponding to sort of strong dependencies between the x1 and x2 coordinates. And there are different extensions, and many of these are trying to tackle this limitation as well. So one extension is that we can do a random scan. Well, this is not really about the strong dependencies, but we can do a random scan. We don't have to loop over the coordinates in order, but you can select one coordinate at random at each iteration and update that one. We can also have blocks of variables, as I said. So each xj could be a chunk of variables in your original models. And these blocks can also be overlapping. So you don't have to update this joint set of variables at each iteration. I could update, say, x1, x2 jointly, and then I can update x2, x3 jointly in the next step. That's fine. As long as all of these distributions that we sample from are full conditional distributions under the target of interest. And there's also a possibility of doing collapsing, which is essentially that in some steps of the Gibbs sampler, we marginalize out some variables and sample the remaining ones from their marginals. This has to be done a little bit with care to ensure that it sort of remains valid, but it's possible to do that. Gibbs sampler now, which at each iteration in the internal sort of inner loop of the Gibbs sampler, it takes some chunk of variables from I, and then updates those by sampling from the full conditional distribution over those variables conditionally on everything else. That's what one step of the Gibbs sampler does. But in many cases, even these conditionals can be difficult to compute exactly and sample from exactly. But we can still make use of the same idea with Gibbs sampling, but instead target these conditionals using some other MCMC procedure. The point with this is that we can then take this high dimensional problem that we started with and break it down into a sequence of lower dimensional problems, and then we can design MCMC samplers for lower dimensional conditional. And also in many cases, some of these conditionals sample from exactly, whereas some others might be harder to derive analytical expressions for, and then we can use some, say, Metropolis Hastings step for those conditions. So yeah, one example of this is to then make use of Metropolis Hastings. Specifically, would then construct a Gibbs sampler where at iteration j, sort of in this inner loop, where we want to update this variable xj conditionally on everything else. And here I use this shorthand notation x minus j. This just refers to all other variables. I want to sample from this conditional, but assuming that this is now not available, I can instead sample xj from some Markov kernel kappa j. It's a distribution over the xj coordinate. It's possibly depends on all other variables and the previous value of xj, because this is not constructed as an MCMC kernel, but it should be such that it leaves this exact conditional invariant. And this is an example of what this might look like. Here we have sort of a complicated distribution over two variables where the conditional over x2 given x1 is constructed to be simple, but the conditional over x1 given x2 is complicated because we have this non-linear function appearing here. And then we can then apply a MCMC kernel internally in this Gibbs loop to update coordinate x1. And the resulting algorithm will then look something like this. So just showing you this as one example of how we can combine different MCMC procedures to construct some more complicated algorithm in a correct way. So I will not actually use this idea of Metropolis within Gibbs as an example of, but we will use other ways of combining MCMC kernels. Okay. With this background on Gibbs sampling, let's talk about how we can use Gibbs sampling in the context of dynamical systems and state space models in particular. So if we look at an example here, we have a linear Gaussian system again, very simple one, but just to show you the idea, we have some unknown variances here, theta 1 and theta 2, and we want to compute this posterior distribution over the thetas given some batch of observations. Then targeting this posterior distribution directly using the Gibbs sampler is difficult, and the reason for that is that we have these latent state variables, the x's as well, right? So in order to target this, we would still need to compute this posterior distribution to get the conditionals of this. So what we can do instead is to introduce these latent state variables as auxiliary variables. And I mentioned that possibility already before when introduced this notion of auxiliary variables, that sometimes they actually have a connection to the model, and this context here with the state space model, the states are a natural candidate for auxiliary variables in the sample. So we will instead target this joint posterior orbit theta and x. And we will then group these variables together so that we sample all the x variables jointly from their conditional distributions and then this distribution conditionally on theta and y. And then we will sample the theta from its conditional distribution given x and y. In some sense, a two-stage Gibbs sampler, but in each step of this, I'd rather you sample more than one variable or one chunk of variables. The first step here, and again, in this linear Gaussian setting, be using Kalman filtering techniques and Kalman smoothing techniques. So there are ways, I'm not sure if that's something that you have discussed, but there are ways using Kalman filters, that we can actually sample from this exact smoothing distribution. Essentially, you run a Kalman filter forward in time until capital T, and then you run a backward simulation method to step your way back in time and generate a sample trajectory from the full joint smoothing distribution. And then in the second step here, we want to sample the parameters. Well, here in this example, I assume that we had some inverse gamma priors. And the reason for that is that this turns out to be a conjugate prior for this Gaussian likelihood that we have in the linear Gaussian state space model. So we can actually work out what these conditionals are. If I now condition on both the states and the observations, then I obtain some closed form expressions for those full conditionals. But as I said before, if that would not have been the case, then I could still target this using some kind of Hastings kernel, for instance. Theta is now hopefully a sufficiently low dimensional variable so that I could do that. But in this example, we can now simulate exactly from their inverse gamma posteriors. If I do that, I get some sample trajectories looking like this, and we can see that we have a rapid sort of convergent phase first, and then we start sampling from the posteriors. And doing this for a long time, we get some posterior histograms, just collecting the samples from the SMC chains. Okay, so this is now an example of or a model where we could apply this Gibbs sampler exactly, where we alternate between sampling the x's and the thetas. But as before, we're interested in general nonlinear, non-Gaussian dynamical systems. So if we now have a model of this form, I still want to apply a Gibbs sampler where, for example, the thetas given the x's and then the x's given the thetas in this way. We will assume that this first step here is still okay. That sampling the theta, if I condition on both the states and the observations, is a somewhat easy problem. So I will not talk about that part. You can kind of imagine that if we have a state space model, sampling from this thing is assuming that the states are known. That is the meaning of conditioning on the states. And doing parameter inference in a state space model, if you assume that the states are known, that's a much easier problem than so hopefully you can sort of accept that this is, in many cases, quite okay. But the second step here, sampling the states from their conditional distribution, the joint smoothing distribution, even for a fixed value of the parameters, that is typically a hard problem. Okay, so let's see if we can do something similar to before. Then we took, well, in the Metropolis Hastings case, we took this sort of ideal Metropolis Hastings algorithm, and then we just replaced the difficult part with a particle filter estimate. Could we do something similar here? So replace sampling here from this exact smoothing distribution by running a particle filter and then using that to sample a state trajectory. So what that means is that at this step of the algorithm, when I want to sample the x, I have a fixed value of theta, the current state of my MCMC chain, parameterize my model using that value of theta. Then I run my particle filter. This will generate a bunch of particles like this, right? With their genealogy as well. So I run that up until the final time point. So capital T here would be 25. And when I'm done, I sample one of the particles at the final time point with probabilities given by their final importance weight. So these W capital T. And then I trace that particle, its genealogy, backward in time. I'll pick out this red sample trajectory and say that this is now a sample which is an approximate draw from this smoothing distribution. And if I do that, I get sort of an algorithm that I could implement. Would alternate between this procedure, sampling the X in this way, and then I update data value, and then I go back to the again, and then I get your sample from X and so on and so forth. But this still gives me sort of just an approximate draw here, and unfortunately, it's not as simple here as in the Metropolis Hastings case that this just happens to work in this way. So we will actually just get an approximate draw in this step, and the quality of this approximation will, of course, depend on the number of particles that I use. If I use too few particles, I have a poor approximation of the smoothing distribution, and this will be quite far from the sample from the thing that I want to simulate from here. So this will not result in a correct MCMC algorithm. It sort of, it's based on the particle filter, which gives me this approximate sample. We will not have the correct joint posterior as a stationary distribution. And for this to work, we would need to have sufficiently large n so that the approximation error completes. And finally, it also means that we do a lot of wasted computations here because we run this particle filter with n particles, and n has to be large. And then we pick out a single trajectory from this. And then we use that to update the parameter theta. But since the particles that we had from before, they were generated using sort of an old value of theta, we can't really reuse those particles. We need to run a completely new particle filter from scratch again. And we do that at each iteration of the MCMC. So we will see if we can now do this in a slightly different way, which addresses these issues. And again, we will use this particle MCMC framework. So this is kind of the starting point for this particle Gibbs algorithm. And we said that it's not really satisfactory because we used just a sample from the particle filter here. So what we will try to do instead is to replace this running a particle filter and just a trajectory by constructing some Markov kernel, kappa, and I have some subscripts n and theta here. N is just to show that this will be constructed using a particle filter, so it depends on the number of particles in that particle filter. So we have this kappa, and it depends on the number of particles, but also on the parameter theta. And this should be constructed in such a way that it has this conditional distribution as a stationary distribution. Now, if I could find such a Markov kernel, and this is now a Markov kernel on the space of state trajectories. So one draw from this would give me a complete trajectory x0 to t. But if I could find such a kernel, then this Gibbs procedure here will be a correct MCMC. So it's one example then of this composition of MCMC procedures that I mentioned before, that you have a Gibbs sampler and then one of the conditionals here happen to be difficult, so we replace that with some other. So the main part now of this lecture will be discussing how we can construct this kernel, which has this property. And if we can find that property or that kernel, then we can plug it into the Gibbs sampler. You can then note that most of the derivations here will be considering this conditional distribution where we condition on a fixed value of theta. So you can kind of assume that theta is fixed for the main part of the lecture now. but in practice, when we apply this, we will of course update theta in this kind of outer Gibbs loop. Before going into the details, here is just an example, again, 10 years old now, but this is one example of a problem where we use this particle Gibbs algorithm to do joint state and parameter inference in a neological model. Okay. Before sort of addressing this problem of constructing a kernel for this space of state trajectories in a state space model, it's useful to see if we can do this in a simpler setting. Specifically, we would work with just importance sampling to begin with, because SMC is really a sequential application of importance sampling. So if we can do it with SMC, then we should be able to do it with importance sampling, and then that will simplify the notation quite a lot and so on. But similarly, since SMC is really applying importance sampling sequentially, if we can derive such a kernel for an importance sampler, then it's there's a good chance that we can actually generalize this to SMC. So maybe that's a take-home message as well. If you want to derive some algorithm involving SMC components, always start with the importance sampling case and see if you can figure out how to do it there. And then generalizing should, in most cases, be possible. So we will work now with simplified setting. We assume just that we have some target distribution pi of x. And the task now is to construct an MCMC kernel for this pi of x, essentially. We have this kappa n, this Markov kernel, which has pi of x as a stationary distribution. And I want to construct this MCMC kernel using importance sampling. And I want to generalize this to the SMC setting. Now, if we think about what the Markov kernel is, well, it's really a conditional distribution over x star given x, but you can also think about this as some stochastic procedure. In particular, if we imagine sampling from this kernel, this is typically then implemented as some function which takes input x and then does a lot of computations internally involving random numbers and then spits out x star. That would be a sample from a Markov kernel. We'll construct this Markov kernel as such a stochastic procedure. And specifically, we define this n using what I refer to as conditional importance sampling, which is this procedure here. So then we take the current state x here, the blue x, as input, and then we proceed using this 5 steps here. So first, well, I said that this is going to be based on importance sampling. So first I draw xi from some importance sampling Poisson distribution q of x. But I only draw n-1 such samples. So n here is still the number of samples, you could say, but I sample n-1 times from q, and then I set the nth sample deterministically according to this input. So this is where the conditional part in the conditional importance sampler. I then compute some importance weights here, W tilde, ratio between target or unnormalized target and the proposal. I do this for all the samples, so including n, which means that I get the weight also for the sample that I have as input to this procedure. I normalize these weights, and then I draw a categorical variable with probabilities given by these normalized importance weights. And then I take the bth particle or sample here and return as an output. And that would be my red x star. The first thing to sort of grasp here is that this is actually implementing a Markov kernel. It implements a way of sampling from a Markov kernel. I have a small illustration here just to show what it looks like. So on the left here, we have kind of what goes on internally in this procedure. And on the right, we have the resulting trajectory of the MCMC algorithm, sort of the Markov chain. We initialize the Markov chain here at 0, which means that we have sort of a conditional sample here at 0. So then one application of this kernel proceeds as follows. So first we generate a bunch of samples from the proposal. That's the yellow line here. Those samples are represented by the gray dots. I compute some importance weights for these generated samples, and the importance weights are the ratio between the target, which is the black curve, and the proposal. Based on those related particles, I select one of them randomly with probabilities given by the importance weight, so the height of these bars. And this will now be the output from the kernel. So this is where the Markov chain will move. So it will move from 0 to this value around 1 here. It jumps up here. And that's one application of the kernel. The second application, I take the current state here, the value that I got out from before. I feed that back into this procedure as my new input. I condition on this blue cross again, generate a bunch of candidate samples, compute weights, and then I get this configuration, this value over here. So the Markov chain jumps up to a value of around 4.
Maybe I'm preempting a bit, but is it possible for the proposal to adapt to the, X you're putting into it, or does the proposal have to be fixed?
No, you can adapt the proposal similarly to how you can do adaptive MCMC. And
it's naively looking at this, it seems quite wasteful.
Yeah, sure. So I mean, kind of showing this as well to maybe amplify the effect of the mismatch here between the proposal and target. So, but trying to show you that this, if we keep doing this, even with this sort of mismatch, if I do this and continue for sufficiently long, I look at the histogram over all the states that I got out from this procedure, it will actually approximate the target. So what I'm kind of hinting at here is that this is indeed a correct or valid MCMC kernel for the target. Yeah. And that is essentially what I show. Next, so a statement about this kernel is that this procedure defines a Markov kernel, which admits pi as or has pi as a stationary distribution of particles, and furthermore that this kernel is under weak conditions ergodic and it converges at a geometric rate towards pi. So we have satisfied both of these basic requirements that we have on an MCMC kernel.
What does THM stand for?
Theorem.
Oh, okay.
Not necessary to abbreviate. Back to the blackboard for proving the first of these theorems. So we'll focus on stationarity, and then maybe I'll comment a bit on the ergodicity. Time for that. So in order to prove this statement that this kernel has pi as a stationary distribution, we will first of all analyze a slightly different procedure, but it's sort of equivalent in terms of the inputs and outputs, you could imagine. It just turns out to be easier to analyze this. So let's start by defining what this equivalent procedure is. And I will split it into 2 steps. So in step 1, we will add one line to this stochastic procedure in which I draw another categorical variable, which is uniform of this index at 1 to n. So draw this variable b, and then I set the b sample here according to the input x. That's the blue. So, and this is the only difference. And hopefully you can then see that this doesn't actually make any difference. I just sort of select a random index and putting my conditional particle or sample on that random index instead of always putting it on the nth. And as I said, it just turns out to be easier to analyze this formulation. Okay, so once we have set the b sample here deterministically to x, I generate the xi's from my importance sampling proposal, and now I do that for all I except coordinate b or sample b. And before I did that for all minus or except n, so up to -1, that's how we skip the b sample here. So that's step 1, and then in step 2, so this is just splitting the procedure into 2 steps because I will analyze them separately. We just continue, and then we compute the importance weight, so it'll be tilde I, which is equal to the unnormalized target, which is called item here, divided by proposal. And that's done for all the particles, including the conditional one. And normalize. And then we draw now another categorical value, B star, on the categorical distribution with normalized importance weights as probabilities. And finally, we return x star equal to x. So what we'll do next to show that this indeed has I as a stationary distribution is to again work with auxiliary variables. We will define an extended target distribution. And the extended target distribution will be over all the random variables generated by the stochastic procedure. And then we will show that the procedure that we have here on the board is actually a Gibbs sampler for this extended target. And then we can rely on the fact that the Gibbs sampler produces a valid MCMC kernel. So we treat all of these variables generated by the procedure, and that would be B. Misleading when I said it in that way, but the B and the excess except the one that as an input as auxiliary variables. And we will define an extended target. Which is now a target distribution over, well, first of all, we have the original target. So that was a distribution over XB, this formulation. And then we have all the auxiliary variables, the excess except all on this variable B. We get now a joint, where we define a joint distribution over x1 to n and B. And this is a definition now, so I will define this in the following way. So first, I will add factor 1 over n. And this is, you can imagine the distribution over, the marginal distribution over the B variable here. So this is categorical variable. And we say this is just uniform over 1 to n as marginal distribution, which is 1 over n. And then I have a conditional distribution over xb, conditionally on the value of b. And I say that conditionally on b, the bth coordinate should be distributed according to the original target of interest. And once I've generated that, I say that all the other x's here, except for b, they should be drawn from q. So this now gives us a distribution over n x values and 1 b index value. And to prove this statement here, I will do facts. So fact 1 is that if x, which is now the input to this procedure, is actually distributed according to the target. So this is usually what we assume when we're talking about stationarity, that assume that we are at the sample from the target, and applying the kernel ones give us back a sample from the target. So we assume that we have a sample from pi, and feed that into this stochastic procedure. Then after step 1, we have, well, in step 1, we generate both the b value and we generate all the remaining x values. So after step 1, we have a sample from this extended target. It's essentially just doing some kind of imputing all the missing values here. Because I said that the input value is distributed according to pi. So if I sample b uniformly, then I get the sample corresponding to this term. Then I set xb equal to the input. Well, the input that was distributed according to pi, and then I just fill in all the missing x values from So that's the first sort of fact that we use here. And then second fact, which now concerns step 2 here of the algorithm, where we compute the importance weights and then we draw B star. Well, second fact here is that step 2 is a Gibbs update. This on B with respect to this joint. We can kind of view this sampling B star here as sampling a new value for B from its full conditional distribution. So conditional distribution pi B star given x one. And that's not completely obvious, perhaps. So to prove the second fact, well, we look at this conditional. Pi b given x1 to n. As always, when we want to derive some stereo distribution like this, it's we note that this is proportional to the joint. So this is going to be proportional to pi b comma x1 to n. And well, this was just the target that we had down here. So it's 1 over n. And then I can multiply and divide by q of xb. And I get pi divided by q here. And then I fill in sort of the missing q of xb in this product. Equivalently write this as pi xb divided by q xb times the product, which is now over all samples. Y goes from 1 to n. Okay, but since we're now actually looking for a conditional distribution over B, we only have to care about the terms here that involve B. We're looking for this up to proportionality, and then we can normalize it to get this distribution. And B only appears in this part here. So this is actually proportional to pi x divided by q x. And even more so, we can plug in the unnormalized target here. We're just working with proportionality anyway. And this happens to be the importance weights. So this is going to be equal to the unnormalized importance weight. If I now normalize this distribution, that just means normalizing the weights. And this is then shown that this distribution is a categorical distribution with probability given by the normalized. And if we put this together, we now have that this procedure, step 1 and step 2, what they actually do is that they take the input value x, we impute all the missing values for this extended target, and then we do a Gibbs update on B, and then we output xb. But according to their extended target, xb is actually distributed according to pi. If the input is distributed according to pi, then so will the output. And therefore we have proven this first theorem. Just so far. So what we've done now is to construct this conditional importance sampling procedure. I showed you that it's Markov kernel, and we also proved that this Markov kernel is sort of a valid MCMC kernel for the target pi. So what we'll do next is to generalize this from importance sampling to SMC. But the principle is exactly the same. So if you can kind of follow this proof, then you can also follow the proof in the MCMC paper to understand why particle Gibbs is a valid MCMC kernel. It just becomes sort of a bit more computationally cumbersome because you have to keep track of all the particles and ancestor weights and so on, but follows the same idea. But just looking at what this then results in, and I will not make any proofs or anything for this particle Gibbs kernel, but just show you what it looks like when we generalize this to the SMC setting. Well, then the state X is now replaced with a full state trajectory. So we have as an input to this Markov kernel trajectory x0 to t. I will refer to this as the reference trajectory. It's just the input to this Markov kernel. And the Markov kernel is now constructed as a distribution on the space of trajectories, right? So it will take one reference trajectory as input, do some internal computations, and then spit out a new trajectory, this red X star. The way this is done is that we run a particle filter. Then we have this kind of conditioning procedure as in the conditional importance sampling kernel. So at each iteration of the particle filter, at each time step, we only sample n-1 particles in the standard way by simulating from their proposal. The nth particle is set deterministically according to the reference. So I set xtn, the nth particle is equal to xt, the blue input. And its ancestor index is set according to, or set equal to n, which means that I essentially keep this reference trajectory intact. If I would look at the genealogy, I would kind of follow that reference trajectory at any time point. So I run this conditional particle filter up until the final time point, capital T. And then I proceed as in the conditional importance sampler. I generate this value B here, which is categorical variable with probabilities given by these final importance weights. And then I trace the genealogy of that trajectory, and that gives me my output X star. So looking at it in an algorithm, this is standard bootstrap particle filter. The difference here is at initialization, sample only n-1 particles as usual, and then set X and deterministically. And then at each step here, similarly, we simulate AT and XT only up until index n-1, and then we set nth particle and its ancestor index. And then, as I said, when we're done, we generate the new trajectory this way. So looking at it in an illustration, it would look as follows. So since we have, this is now a kernel on the space of trajectories, we always input the reference trajectory. It's shown in blue here. So I have this as some kind of starting point for the algorithm. And then I run my particle filter around this trajectory in some way. Some sense. Particles like this, keep track of their genealogy. And then when I'm done, we see that we have a bunch of particles here. These particles, they also interact with the reference trajectory because whenever we resample, there is a chance that we multiply the reference trajectory. It sort of enters the resampling as any other. So the only thing that we know is that we keep the blue line trajectory. That will be one of the trajectories generated by the particle. The other trajectories, they can also interact with the blue trajectory in some way. They can coalesce with it at some point. And we see that happening here actually. And then at the end, we sample one of these black dots over here, and we trace the genealogy of that, and we get X star. And this procedure then gives us one sample from this particle Gibbs kernel. So if we now plug this into the Gibbs algorithm from before, it looks as follows. So I have this kind of loop here, which is just standard CMC loop with 2 steps, and they are similar to this ideal Gibbs sampler. So first we draw theta from its full conditionally on both current state trajectory X and the observations. And then conditionally on this new value of theta, we want to update the state trajectory, and I do that by simulating from this particle Gibbs kernel conditionally on both the current theta value and on the previous sort of reference trajectory. Yes.
Well, just as a thing, so this requires algebraic manipulation in order to obtain the conditional distributions for 2A.
Yeah, exactly. So that is essentially a standard Gibbs move on theta. So that we assume we can do in some way. Either you have this controlled form, or maybe this is simple enough so that you can do some Metropolis Hastings move on this part.
Yeah, but so basically that's just fixed. I mean, it's kind of fixed states, and then we use whatever stats tools we have just to say this is the density, and we pull out the conditionals for that one. So it's not automatic.
No, not really. Depends on the model. I mean, in some situations you can actually derive this if you have some priors for theta here, which is conjugate to this, sort of usually referred to as the complete data likelihood, which is kind of, if we assume that X would be known, then you would have sort of a complete data likelihood over both Y and X. If you have a prior which is conjugate to this, then the posterior will also be available in closed form.
And my thinking is typically for this, you kind of want that because it's much cheaper.
It's cheaper than having some non-conjugate prior mean.
Cheaper than saying, okay, we're gonna have to sample this via, some Metropolis scheme.
Yeah. I think for this presentation, I haven't really focused on this and just assume that this, you can handle that in some suitable way, that it would be possible to implement the ideal Gibbs sampler if there would be some oracle that would give us samples from the state trajectories. And we're then focusing on how we can actually obtain such state trajectory samples in the second step. Yeah, but that's essentially the basic particle Gibbs algorithm. It relies on this conditional particle filter formulation to implement Markov kernel for state trajectories. That is sort of a valid MCMC kernel. It relies on SMC. You've seen a modification of the standard SMC. A few properties here. Well, first of all, this is indeed a valid MCMC kernel. Similar arguments to the ones that we had on the board here for the importance sampling case can be applied here as well to show that this is indeed a kernel that leaves this posterior distribution invariant. And this holds for any number of particles. So it doesn't rely on asymptotics in N to be a valid MCMC kernel. That's kind of, again, thinking about this notion of exact approximation, that we want this to result in a valid MCMC kernel, even though we make an apparent approximation internally. This kernel is also, under weak assumptions, ergodic. For that, we require at least 2 particles, and the reason for this is intuitively that 1 particle is reserved for the reference trajectory. So if we only have 1, then there's no chance of moving. But if we have at least 2, there is a chance that we switch to another particle, or the other particle. And then that allows the kernel to move and therefore be ergodic. Okay, so what's the catch? Why can't we just apply this with 2 particles and then we have something which is like a valid MCMC, and then that's also. Well, we could actually see the problem already in the illustration that I showed you before. Even though this is ergodic for the n larger than 2, the mixing rate of the resulting MCMC, or the mixing rate of this kernel, will deteriorate as t becomes large, unless we have a number of particles that is proportional to t. And the reason intuitively,
It's linear then with so that there's some theory regarding this linearity between n and t.
yeah, exactly, yeah. So I wrote at least here in parentheses. So this rate we get under strong mixing assumptions. If you have worse mixing, then you probably need to have, I mean, if you don't have any mixing in your state space model to begin with, then I would say that this should be exponential, because then you're essentially doing very high dimensional importance on these state trajectories that don't have any forgetting. So, yeah,
It is
best
because
case it will be linear.
the problem is because the larger the t is, the more times at each time step you give the possibility to each trajectory to replicate the reference trajectory, then not moving from that.
Yeah. So you can kind of see that in this illustration, right? That if I apply this with some reference trajectory in blue here, I run my conditional particle filter. The conditioning also in some way means that we are conditioning on this reference trajectory to survive. So we're kind of always injecting that as one of the particles that sort of be generated and that will survive the resampling step. And as you know by now, the particle filter has this path degeneracy issue that as you go back in time, if you start tracking the genealogy of the particles, they will start coalescing. So, and at some point they will have a common ancestor. That happens here. But in the conditional particle filter, there is only one possibility for what that common ancestor is, because we're injecting the reference trajectory here. So they will always coalesce with the reference trajectory at some point. And if you go further back, you see that the red curve here is identical to the blue curve. And this means that for time points early, sort of in this trajectory, the probability of moving goes to 0 as t becomes large, if we have sort of a fixed number of particles. So this is the degeneracy of the kernel, as I said, that we require this, at least this linear scaling, to prevent this from happening, to have at least the non-vanishing probability of moving at time 0. And we can see this also in numerical examples. So here's it's a toy model, but now it's a non-linear model. It's a stochastic volatility. It's a one-dimensional state like this, and a non-linear observation. And I run here, simulate some data. Here I have 100 time steps in my synthetic data. And I run this particle Gibbs algorithm with 1,000 particles in the particle Gibbs kernel, and I do this to infer this unknown variance here. So apply this alternating between data and X and so on. And then we get an autocorrelation function, which looks like this. And if you remember from before, I said, if this drops to 0, then we're happy. This seems to work quite well. But now we have quite many particles as well. It's 1,000 particles, 100 time steps. If I reduce the number of particles to 100, it's still there will be an increase in the autocorrelation function here. If it goes down to 20 or 5, something really extreme here, we can see that the autocorrelation function is really and the reason for this is the degeneracy issue, that if I have 5 particles, apply that to a time series with 100 time steps, the probability of not having a coalescence at time 0 is pretty much 0. Even worse, if I increase t, then even with 100 particles, we don't have any convergence here. So it really becomes critical that we have sufficiently many particles for the problem. This is a bit discouraging. It's still an algorithm that works quite well, and it can sort of solve problems that couldn't be solved at all before this method was introduced, but still a bit discouraging. And this leads me into some extensions of this algorithm, and I will talk about one such extension called ancestor sampling, which really tries to tackle this issue, see if we can come up with better scaling laws essentially for these particle kernels. So this is an extension, meaning that I will now modify this algorithm a little bit further, but it's only a small modification. So if we look at the particle Gibbs procedure, we said that each iteration or application of the particle Gibbs kernel, we input this reference trajectory, sample n-1 particles in the usual way. The nth particle is set according to xtn is equal to this reference xt, and then I set its ancestor index n equal to n. This means that the ancestor of the blue xt will be the blue xt minus 1. So in ancestor sampling, the only thing that we change in the algorithm is this last step here, where we sample set the ancestor index deterministically, and instead we will generate a sample for this variable stochastically. Specifically, I will sample this ancestor index for the nth particle, that is the reference particle, with probabilities given by this expression here. And you can think about this as essentially applying Bayes' rule to figuring out which ancestor that this reference xt came from. So if we are at time t in the particle filter, at the previous time step we had n particles that are all weighted according to these importance weights, the wt minus 1. So that can be thought of as a prior distribution for each, prior probability for each possible particle that we had at the previous time step. And then we have this transition density here, which tells me how likely is it to transition from any particle that I have at time t minus 1 to the reference particle that I have at time t. And since xt is fixed here, we can think about this as a type of likelihood term. Then we have product, prior, and likelihood. We normalize this to get posterior distribution over which ancestor did we have at. Kind of reassigning the ancestors for reference particles. And yeah, this is kind of the intuitive explanation, but it can of course also be shown formally that with this modification, we still have the same properties, the same validity that we had from before, that we have the correct stationary distribution, we have ergodicity and so on. So what effect does this small modification of the algorithm have? Well, if we have the same example as before, we have a reference trajectory in here, and then we run the particle filter, conditional particle filter with ancestor sampling. We instead get something like this. As you can see here in this illustration, what happens is that we kind of break this reference trajectory into pieces. And what I'm plotting here is each line, each blue line here is pointing from the reference particle to its newly assigned ancestor. Since these ancestors are they're sampled from all the gray dots here, that can result in kind of breaking the reference trajectory. Okay, so we get something looking like this. Looking at the particles here, we see that they still have the path degeneracy issue. They are still coalescing at some point. So this modification of the algorithm, it doesn't solve the degeneracy issue of the particle filter itself. But if we now pick one trajectory here at the end and trace that genealogy, there's a good chance that this will now be something different from the reference trajectory. And if we plot the two trajectories on top of each other, that becomes more apparent. That even with this sort of ancestor sampling step, we have degeneracy, but we will degenerate towards something else than the input. And this allows the sampler to be. And that becomes also very clear when we now try this on numerical example. So again, this situation with the stochastic volatility, we had 1,000 time steps here, and this is what it looked like for the standard particle Gibbs. Going below 1,000 particles, it kind of breaks down. But if you just add this ancestor sampling step, you can actually solve this pretty, 5 particles is more or less sufficient to get something which is close to the optimal performance, which would be the limiting performance here of the ideal Gibbs sampler applied to this problem. For those of you who will be here for the workshop next week, I do believe that there is a talk by Anthony Lee who will address this from a more theoretical perspective, not for this algorithm, but for a related algorithm to show stability properties of this. Okay, some practical considerations and also extensions, I should say. But maybe one thing, if you want to implement this yourself, is that you need to be a little bit careful when implementing the resampling step if you have this conditional particle filter. A common implementation of how you would actually implement this sampling the ancestry indices for all particles except the nth one would be that you actually apply your standard resampling procedure. You store all of these ancestor weights that you generate, and then you just overwrite the nth one according to the conditioning, or if you want to have ancestor sampling, you would simulate a new value for this. But a problem with this is that common implementations of resampling give you an ordered list of ancestors, which means that this will actually bias towards always overwriting the high sort of large indices. And that will give a bias in the algorithm. It's something that can be easily fixed by just randomly permuting these ancestors before overwriting one of them to make sure that you don't always overwrite the same indices. That's something to be aware of. Similarly, if you want to apply some low variance resampling algorithm like stratified or systematic and so on, these ancestor indices are no longer conditionally independent. You sample all ancestor indices jointly from some joint distribution, which is marginally biased, but it's they're not independent. And the derivation that we have validity of this kernel assumes independence. So this is something that can be fixed, but it's also something that you need to take into consideration, and you need to make some adjustments to the resampling. Okay, moving on with more extensions, it can be interesting to note that the way I presented particle Gibbs now is really as an algorithm which implements a Markov kernel, which has particular properties. This also means that we can use this kernel freely in more like composite algorithms as just one component. So for instance, if you would have some kind of coupled dynamical systems, or not coupled maybe, but multiple dynamical systems that share parameters in some way, then you can easily apply particle Gibbs to this by just designing a kernel for each sort of system or model here separately. And then you can update the X values here using a particle Gibbs kernel. You update the X values here using another particle Gibbs kernel, and then you can just combine the outputs from those to make a joint update of the shared parameters. And you don't have to sort of put everything into the same extended target formulation, because we have proven these properties for the kernel itself. This also means that you can adjust the Gibbs sampler itself. So now I showed you or spoke about Gibbs sampling for state space models as alternating between sampling the thetas conditionally on X and the X's conditionally on thetas. But it's also possible to do other type of Gibbs moves or Gibbs updates on the X variables themselves. So one example of this would be to do some kind of blocking. So if you imagine that we have just a single time series again, we have some parameters, we have some states. But since we had this degeneracy issue with the original particle Gibbs kernel, if the number of time steps becomes large, one way in which we could try to address this issue is to divide the state variables into some blocks, and then you update one block at a time. And these blocks could, for instance, be overlapping. So if we have entire time interval here from 0 to capital T, we divide this into 5 blocks like this, and then you implement one particle Gibbs kernel for each block separately, and then you just alternate between sampling one block conditionally on the other ones until you have updated all. An interesting aspect of this is that if you have blocking like this, you can actually do parallel updates as well, because if I condition on J1, J3, and J5, then J2 and J4 will be conditionally independent. I can apply those two Gibbs kernels, particle Gibbs kernels in parallel. And then similarly, when I condition on J2 and J4, I can update J1 to J5, or J1, J3, and J5 in parallel. And this is something which also deals with this sort of degeneracy issue. And here you can then show that you get sort of a stable algorithm, and we only need to select the number of particles in each block here proportional to the block size, which makes sense because we're constraining the number of time steps that we're updating. Okay, this is a slide with a lot of text, but just summarizing essentially what we have covered. We're about particle MCMC. It's a way to construct MCMC kernels for this joint posterior. That's a type, of course, it should be using SMC. But these kernels, they are built on an extended target construction. So we define sort of an extended distribution which has this original target as one of its marginals, and then we apply more or less standard MCMC kernels on that extended target. Depending on which MCMC method that we use on the extended target, we end up with different MCMC algorithms. In the particle Metropolis Hastings, we use a Metropolis Hastings algorithm for the extended target, and we have this MH proposal, which has a particular factorized form this way. So, and that was needed in order to get the cancellation of these intractable psi terms here. The particle Gibbs kernels is based on doing some Gibbs sampling on the extended target. And this Gibbs kernel, yeah, it has this sort of modularity that we can combine it with other MCMC kernels quite generally. ancestor sampling as one extension of particle Gibbs, which small algorithmic modification, but it can have a large impact on the practical sort of performance.
In the case of multiple dynamical systems, I'm curious, how do you fuse the information about theta?
Here, you mean?
Yes.
I think it depends on what, how this data is shared sort of between these. But you could imagine, for instance, that you have similar looking dynamical systems here, so that you have conjugacy between each complete data likelihood and theta, and then fusing information is essentially just summing up all the sufficient statistics for these models. But yeah, I mean, we worked a little bit on something similar to this, but then we actually had different thetas here that were shared between different subsets of the but then we did something along those lines. I guess that this was mainly meant to show sort of an example of what you can do with this kind of kernel view of the algorithm.
This is something really obvious that I missed, but why are we sometimes using the Gibbs over the Metropolis Hastings? What?
Yeah,
Do they only work in different scenarios, or is one?
I don't think that's obvious at all. I think it depends on the problem at hand, which method that works best. So there's no silver bullet that always outperforms all other methods. So I think it's similar to sort of why do we have different MCMC methods in the first place? But you can sort of, they have different properties. If you take particle Metropolis Hastings versus particle Gibbs, then, well, in both cases, the algorithm, they are kind of trying to approximate some ideal MCMC method, right? So the first question then is, which ideal MCMC method would work best, assuming that you could implement it? And the Gibbs algorithm, so back to this thing, right? So in particle Gibbs, we're trying to mimic this Gibbs sampler, which alternates between sampling thetas and x's. So if theta and x are strongly dependent, then this ideal sampler will also mix slowly. And then particle Gibbs is kind of, it's limited by the performance by the ideal sampler, so it can never do better than that. And that's also what I kind of meant when I showed you these autocorrelations. Here. We can kind of see that as I increase the number of particles here for PGAS, it's the autocorrelation function seems to converge to some kind of limiting behavior. So now we only have this up to 1,000 particles, but even if I would run this with a million particles, I would get something very close to the green line. And that is kind of the performance of the ideal Gibbs sampler that we could not implement, but that we're now approximating. And if that is not working well, then this particle Gibbs algorithm will also not work well. And then maybe particle Metropolis Hastings is a better choice. There you don't have this alternation between x and theta. You're trying to sample the theta directly sort of from its marginal. But then again, you're limited by sort of, you need to have a proposal distribution in theta. You also need to have a sufficiently good likelihood estimator. So you have something similar to this situation that we need to scale n linearly with t to get that to work. If you remember from before the break, we had this central limit theorem for the likelihood estimator, which showed that you need to have this kind of scaling. And there's no simple way that I'm aware of getting something similar to this kind of very efficient sort of scaling in the number of particles that, or that you actually get the working method even with as few as 5 particles. I don't think that is possible for particle Metropolis Hastings.
Have you done any investigating into